In this video, we're going to learn how to find and classify critical points of autonomous systems according to their type and stability. We'll then walk through an example of each type: a saddle, node, spiral, and center. Let's get started. We're going to begin by learning how to find critical points of the following autonomous system of differential equations. dx dt is equal to a function f of x and y, and dy dt is equal to a function g of x and y. This system of equations is called an autonomous system because the right-hand sides depend on x and y and not on time t. Let's now define what a critical point is. A critical point is a point that I'll call x sub 0, y sub 0, where the system is in equilibrium. This is where both derivatives, dx dt and dy dt, are equal to 0. At equilibrium, there is no change in the system. To find a critical point, you just need to follow these two steps. The first step is to set both dx dt and dy dt equal to 0, and then the second step is to just solve for x and y. Let's walk through an example so that you can see how this works. We're given dx dt is equal to 2x minus y, and dy dt is x minus 3y, and we're going to find the critical point. The first thing that we're going to do is we're going to set dx dt and dy dt equal to 0. So we have 0 is equal to 2x minus y, and then we have 0 is equal to x minus 3y. In step 2, we're just going to solve for x and y. This equation gives us y is equal to 2x, and then we can substitute that in to our equation here on the right. This gives us 0 is equal to x minus 3 times 2x. This means that 0 is equal to minus 5x. This gives us x is equal to 0. If we come back over here to the left, we plug in x is equal to 0, we get y is also equal to 0. This means that our critical point is equal to 0, 0. Over here on the right, I've included what's called a phase portrait of this linear system. A phase portrait just shows the system's solution curves. Let's go ahead and put in the critical point. The critical point is at the origin. And notice that the solution curves are flowing around this critical point because our critical point is our equilibrium point. We're now going to learn how to classify critical or equilibrium points according to their type and stability. This is going to help us understand how solutions behave near a critical point. For example, over here on the right, we have a system of autonomous differential equations that has a critical point at the origin. Classifying this critical point is going to help us understand how solutions behave near this point. To classify a critical point, we need to rewrite the linear autonomous system in matrix form. A system that looks like this, dx dt, is equal to a function f of x and y, and dy dt is equal to a function g of x and y. Written more specifically like this, where we spell out what f and g are, looks like this when you write it in matrix form. This is just the derivative of vector x with respect to t, where vector x is our vector xy, and it's equal to a times x plus a constant vector b. I highlighted matrix A in yellow because that's what we're going to be focusing on. The eigenvalues that we'll call lambda of our matrix A are what determine the type and stability of each critical point, and they can be found from this characteristic equation that I've written right down here. This equation is lambda squared minus the trace of our matrix A, that's just where you take the mean diagonal elements and you add them, times lambda, plus the determinant of matrix A. And then you set all of that equal to 0. Solving this equation for lambda, the eigenvalues, tells you everything about the critical point, its type, and its stability. If the eigenvalues are real and are opposite in sign, you get a saddle point. And if they're real and both negative or both positive, you get what's called a node. If they're complex and have a real part that is not equal to 0, it can be negative or positive, you get a spiral. And then lastly, if you have an eigenvalue that is purely imaginary, that means the real part is equal to 0, you get a center. Now let's talk for a minute about stability. We'll start with the term asymptotically stable. A stable node and a spiral sink are asymptotically stable, and that means that solutions move toward the critical point. The next type of stability is called stable. A center is stable, and that means that solutions that start near the critical point remain near it. Lastly, we have unstable. There are 3 types that are unstable: a saddle point, an unstable node, and a spiral source. And unstable means that at least some solutions move away from the critical point. Let's now look at some examples. We're going to walk through 4 examples, one of each type: a saddle, a node, a spiral, and a center, where we're going to find the critical point or points of an autonomous system of differential equations. We're then going to classify the type and stability of each point. In our first example, we have dx dt is equal to 2x minus 2, and we have dy dt is equal to minus y plus 1. I've written down 3 steps that we can follow, and we'll start with the first one. We're going to find the critical points by setting both dx dt and dy dt equal to 0, and then we'll solve for x and y. Dx dt is 0, so we have 0 is equal to 2x minus 2, and then we'll set dy dt equal to 0, and that gives us minus y plus 1. Solving our first equation, we get that x is equal to 1, and then our second equation also gives us that y is equal to 1. So we know that our critical point is the point 1, 1. Let's now look at our second step. That step is to rewrite the system in matrix form and then find the eigenvalues. We'll start by putting x and y into a vector. So this gives us the derivative with respect to time of x and y. And now what we're going to do is we're going to pull apart the constants from the x and y. So we have 2, 0, 0, minus 1, and that multiplies xy. And then we're going to have our constant vector, which is going to be minus 2, 1. We need to look at this matrix right here, and we're going to call that matrix matrix A. So we say that A is equal to 2, 0, 0, minus 1. Now we want to find the eigenvalues. The characteristic equation that we're going to use is lambda squared minus the trace of A times lambda plus the determinant of A is equal to 0. If you're thinking, but wait, that's a diagonal matrix, there's another way we can do this, just hold on, because we're going to do that way in a minute. I first want to show you how to do it this way. We have lambda squared minus the trace of A. My students always forget what that is. It's just the mean diagonal entries added together. So this is 2 minus 1 times lambda plus the determinant. Determinant is the main diagonal entries multiplied. So that's 2 times minus 1 minus the off diagonal entries multiplied. And we set that equal to 0. So this gives us lambda squared minus lambda minus 2 is equal to 0. To find lambda, all we have to do is factor this. We can factor this as lambda minus 2 times lambda plus 1, set that equal to 0, and we get that lambda is equal to 2 and negative 1. Before we go on to step 3, let's go back up here and let's look at this matrix again. It is a diagonal matrix. A diagonal matrix is when you just have entries, they can be 0 or not 0, along the main diagonal, but then all the other entries are equal to 0. When this happens, you can just read off the eigenvalues because the eigenvalues are just going to be the entries along the main diagonal. If you can spot that right at the beginning, that will save you some time. Let's now go to step 3. Step 3 is to use this chart and classify the type and stability of each critical point. Down here, I'm going to remind us that our eigenvalues were 2 and negative 1. 2 and negative 1 are real numbers and they are opposite in sign. So if we go up here to our chart, we can see that our eigenvalues are real, opposite signs, and that tells us that our critical point is going to be a saddle point and it's going to be unstable. So let's just write down for our solution that we have an unstable saddle point. Just so you can understand this better, I have included the phase portrait of the solutions of this system. Our critical point was the point 1, 1. So let's go ahead and let's add this to our diagram. There's our critical point. And this critical point is our unstable saddle point. Let's try to understand this a little bit better. Our dominant eigenvalue, lambda 1, is equal to 2. That's always the largest eigenvalue. And that is greater than 0. If you've taken linear algebra, you know how to find an eigenvector that corresponds to this eigenvalue. And what you end up with is the vector 1, 0. This means that our unstable solutions, and I say unstable because our eigenvalue is greater than 0, our unstable solutions are going to point in the horizontal direction. Let's go up to our graph and I will highlight this. Here's the horizontal direction from our critical point. Notice that when our solutions are moving in the horizontal direction, they are going away from the critical point. Now let's let our second eigenvalue, lambda 2, be negative 1. This is less than 0. The eigenvector that corresponds to this eigenvalue is equal to the vector 0, 1, which is the vertical direction. Let's go ahead and write that down. This is our vertical direction. Solutions moving in the vertical direction, that's this direction or this direction, these are going to be stable because our eigenvalue is negative. So notice, if we're moving in the vertical direction, we're moving towards the critical point and not away from it. I've summarized this right down here. Along the vertical direction, the solutions move toward the critical point, and along the horizontal direction, they move away, creating our saddle shape. Let's pull this down so you can see it. It looks like a saddle. For our second example, we have the system of equations dx dt is equal to minus x plus 2 and dy dt is equal to minus 3y plus 6. Just like we did for our first example, we're going to begin by finding the critical points. We're going to set dx dt equal to 0, so we have 0 is equal to minus x plus 2, and then for dy dt we also have 0, and that is equal to minus 3y plus 6. Our first equation gives us that x is equal to 2, and then our second equation gives us that y is equal to 2. So our critical point is equal to 2, 2. In step 2, we're going to rewrite the system in matrix form, and we're going to find the eigenvalues. Our system looks like this. We have d dt of vector xy, and now we pull apart the constants from our x and y. So we have a minus 1, 0, 0, minus 3. We multiply that by xy, and then we have our constant vector 2, 6. This matrix right here, we're going to call matrix A. And I'm going to go ahead and rewrite it because it's what we're going to be looking at. Our matrix A is minus 1, 0, 0, minus 3. Now we can find the eigenvalues. Notice that this matrix is a diagonal matrix, and we can just write down the eigenvalues because they are the diagonal entries. So we have that lambda is equal to minus 1 and minus 3. In step 3, we are going to use this chart to classify the type and stability of our critical point. And let's just put here that our critical point is the point 2, 2. Our eigenvalues right up here are both negative, so we can find that down here in our chart. Our eigenvalues are real and negative, so that's right here. That means that our critical point is going to be a stable node, and we say that it is asymptotically stable. That just means that solutions are going to move toward our critical point 2, 2. For our solution, we want to say that our critical point is an asymptotically stable node. And there's our solution. Let's now look at the phase portrait so we can understand this a little bit better. Our critical point is equal to 2, 2. So let's go ahead and let's highlight that. Here's the point 2, 2. And we know that this point is asymptotically stable. If we let our first eigenvalue be equal to lambda 1, we're going to make this negative 1 because that's the largest eigenvalue. Notice that this is less than 0. The eigenvector that corresponds to this eigenvalue is the vector 1, 0, and this is the horizontal direction. This means that because our eigenvalue is negative, solutions are going to be moving toward our critical point in the horizontal direction. Similarly, our second eigenvalue is also negative. The eigenvector that corresponds to this eigenvalue is the vector 0, 1, and this is the vertical direction. So if we go back up here to our graph, we can see that along the vertical direction, solutions are going to be moving also toward our critical point. I've just summarized this right down here. Along both the vertical and horizontal directions, solutions are going to move toward the critical point. And that's what happens when you have a stable node. Let's now look at our third example. We have the system of equations dx dt is equal to x minus 2y plus 1, and then dy dt is equal to 2x plus y minus 3. Notice in this one, we have an x and y in both equations. In step 1, we are going to find the critical points. We're going to set our derivatives equal to 0. So we have 0 is equal to x minus 2y plus 1. And then we have 0 is equal to 2x plus y minus 3. I'm going to solve this first equation for x. X is equal to 2y minus 1. And then I'm going to substitute that x into our second equation. So we have 2 times 2y minus 1 plus y minus 3 is equal to 0. Let's see. This is 5y minus 2 minus 3 is equal to 0. So we have 5y is equal to 5. Oh, that's nice. So we get y is equal to 1. And then if we go back up here, this gives us that x is equal to 2 minus 1, and it's also equal to 1. So our critical point is equal to 1, 1. In step 2, we are going to rewrite our system in matrix form and find the eigenvalues. This gives us d dt of our vector xy is equal to, pulling apart the constants from the x and y, we get 1 minus 2, 2, 1. This multiplies xy. And then we have our constant vector that comes along for the ride. This is our matrix A. I'm going to rewrite it because that is the important part. 1 minus 2, 2, 1. This one is not a diagonal matrix, so we are going to need to use the characteristic equation to find lambda. Our characteristic equation is lambda squared minus the trace of matrix A times lambda plus the determinant of A is equal to 0. So this is lambda squared minus the trace is just the sum of the diagonal entries. So that is 1 plus 1 times lambda. And then our determinant is the main diagonal entries multiplied. So that's 1. Subtract off the off diagonal entries multiplied. That's minus 4. That's equal to 0. Let's come up here. This gives us lambda squared minus 2 lambda plus 5 is equal to 0. We're going to need to use the quadratic formula to factor this. So we have lambda is equal to negative b, so that's minus a negative 2, so we have 2 plus or minus the square root. B squared, that is 4, minus 4ac is 20. And we're going to divide this by 2. Lambda then is 2 plus or minus. Let's see, inside our square root, we are going to have minus 16. If we take the square root of that, we get 4i. So we have 2 plus or minus 4i over 2. So lambda is equal to 1 plus or minus 2 times I. Let's now classify this. That's down here in step 3. We're going to look at our chart and find the type and stability of our critical point. And I'll just remind us that our critical point is our point 1, 1. Up here on the right, our eigenvalue is complex. And notice that the real part of lambda is equal to 1, and that's greater than 0. So we have a positive real part. Looking down here at our chart, that's this case right here. Our eigenvalue is complex, and we have a positive real part. This means that our critical point is a spiral source, and it is unstable. So let's write down for our answer that we have an unstable spiral source. Let's now look at the phase portrait to understand this a little bit better. Our critical point is equal to 1, 1. And I'm just going to put here also that our eigenvalue is 1 plus or minus 2i. Let's highlight our critical point. That's the point right here. And we know that this point is an unstable spiral source. Our solutions spiral outward away from the critical point. And you can see that they are moving in a counterclockwise direction. Let me show you how you can know this for sure. What we're going to do is we're going to pick a test point. I am going to pick the point 2, 2 just because it's easy. That point is actually right here, but I'm just going to pretend it's right here because I don't have a solution curve drawn at that point. So we're going to write down here that x is equal to 2 and y is equal to 2. What we do is we're going to work with our system of differential equations. So that system was dx dt is equal to x minus 2y plus 1, and dy dt is equal to 2x plus y minus 3. All we're going to do is substitute in x is 2 and y is 2. This gives us 2 minus 4 plus 1, and that is negative 1, which is less than 0. Our second equation gives us 4 plus 2 minus 3. That's equal to 3, and it's greater than 0. So we found that dx dt was less than 0. So that means that x decreases, which means it's going to move to the left. And then we found that dy dt was greater than 0. So that means that y increases. And that means that our solution is going to move up. So this means that our solutions spiral outward in the counterclockwise direction, up and to the left. Let's look at our last example. We have dx dt is equal to minus 2y plus 2, and dy dt is 2x minus 4. Let's find our critical points. We're going to set our derivatives equal to 0. So we have 0 is equal to minus 2y plus 2, and we have 0 is equal to 2x minus 4. This first equation gives us y is equal to 1, and our second equation gives us x is equal to 2. So our critical point is equal to the point 2, 1. Now we're going to rewrite the system in matrix form and find the eigenvalues. Our system looks like this. We have d dt of x and y. Separating the constants from x and y, we get 0 minus 2, 2, 0. That multiplies xy. And then we have our constant vector along for the ride, 2 minus 4. This is our matrix A. So we have A is the matrix 0 minus 2, 2, 0. It is not a diagonal matrix, so we need to use the characteristic equation, lambda squared minus the trace of A times lambda plus the determinant of A is equal to 0. This gives us lambda squared minus the trace is the sum of the diagonal entries, so that's 0. So we're going to have a 0 times lambda. And then our determinant is going to be 0 minus a negative 4. And that's equal to 0. Let's come up here. This gives us lambda squared plus 4 is equal to 0. So we have lambda squared is minus 4, and lambda is plus or minus 2i. Our lambda is complex, and it is purely imaginary. Let's now classify our critical point. Our critical point is the point 2, 1. We need to find in our chart where we have purely imaginary. It's right down here. That means our critical point is going to be a center, and it is stable, not asymptotically stable. Down here, I'm going to write our classification. Our critical point is a stable center. Let's now look at the phase portrait. These centers are pretty interesting. Our critical point is our point 2, 1, and our eigenvalues are plus or minus 2i. Let's go ahead and let's highlight our critical point. Our eigenvalue has no real part, so our solutions are not going to grow or decay. They just orbit the critical point forever in closed loops. You can see in the diagram that I've already added arrows to this, so you can see that our solutions are orbiting counterclockwise. But let's walk through how to get this. Let's pick a test point. I'm going to pick the point 3, 2, and that's about right here. So we're going to let x be equal to 3 and y be equal to 2. Our system was dx dt is equal to minus 2y plus 2. Plugging in y is equal to 2, we get minus 4 plus 2. This is minus 2, and it's less than 0. So dx dt is negative. That means that x decreases, and the solutions move to the left. Likewise, we had dy dt, and that is equal to 2x minus 4. Plugging in x is 3, we get 6 minus 4, which is 2. That's greater than 0. So dy dt is positive, so our y increases, which means our solutions are going to move up. This means that our solutions are going to move up and to the left, which results in a counterclockwise rotation. And that's it. You now know how to find critical points of linear autonomous systems of differential equations, and also know how to classify the critical point according to its type and stability. In the next video in this series, we're going to learn how to find and classify critical points of nonlinear autonomous systems of differential equations. If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.